Hello everyone, welcome back to the lecture. So we're going to continue on from our previous lecture topic is the hypothesis testing from chapter 8. Last time we basically started developing hypothesis test, and we were testing claims about the population mean. At that time, I emphasized that we knew what sigma was. The sigma is the population standard deviation. So we knew something about the population prior. We probably, in order to calculate the standard sigma standard deviation, we had to know what the population mean was. But now it's shifted. So that was, I knew what it was. I think things have changed. I make a claim, and then I do a hypothesis test using as much information as I did. I had no reason to believe that the population standard deviation had changed. If there's anything I know about the population, I would like to use it. You should use it. In this case, in this section 8.3, we don't know what sigma is. So this is a brand new statistic parameter that we were talking about. We just think something, or we get a claim from, let's say, a commercial, a politician, and we want to go back and test that claim. There's no information that we know about the population parameter value. Okay, so this is what section 8.3 is about. Hypothesis test for a population mean. I'm still talking about the population mean at this time. Sigma is unknown. If we don't know the population standard deviation, we get it from the sample that we use to do our test with. Okay. So let's get started. So our objective: test a hypothesis about a mean using the p-value method. We talked about the p-values before. So here we're going to do a hypothesis test. I'm going to slide me down here to keep it so I can read through this. We have an example. Suppose that in a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was X bar, that's from the sample, 2.2 kilograms, with a sample standard deviation of S is equal to 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0? So can we do that? Okay, so we go through, we're going to do the very same thing, but in this case, notice that we don't see sigma. All we see here is S. So this is a brand new study. We have no previous information about the population standard deviation. So we're starting with a different type of test. The structure is going to be the same. We're going to do a claim, a complement. We're going to assign our null hypothesis, our alternate hypothesis. The alternate hypothesis is going to give us what test we're running, left-tailed, right-tailed, two-tail, and then we'll do a sample test statistic based on our sample data. Okay. So let me continue on with the slide, moving it up here. I'm right here. If we knew the population standard deviation sigma, we would be able to compute the z-score of the sample mean to be, and this is how we did the test statistic from last time, x bar minus mu divided by the sigma over the square root of n being the sample size. Use that, we would use that test statistic to perform a hypothesis test. The two methods, the critical value, we would do critical value based on some alpha level of significance. We would sign, here's the critical values, compare the test statistic, were we in the rejection region, the tails, or the fail to reject region in the middle, and who we fell into reject or rejection, always H0, the null hypothesis, the one with the equality, okay? In this example, as is usually the case, we do not know the population standard deviation. To proceed, we replace sigma with the sample standard deviation S, and we use the t-test statistic instead. So the t is the x bar minus mu S divided by the square root of n. So the only thing changes here is S, but this is a T, and instead of a Z-score, it is a T-score based on the student's T distribution, another distribution, right? Okay. We have N-1 degrees of freedom, as we've talked about before. So here is our assumptions that we're going to use. We have a simple random sample. The sample size is large, N greater than 30, or the population is approximately normal. And we'll see in a few minutes that what if we don't know that the population is approximately normal, but we have a small sample size. We would do a dot plot, make sure that there's one of two things. There's no outliers and there's no heavy skewness. Both of those must hold. And then we could kind of assume. We would rather have a large N greater than 30 or know that the population is approximately normal. So here was this case. We have the X bar is 2.2, S is equal to 6.1, N is equal to 76, and we wanted to know if the mean weight loss mu is greater than 0. So as a mathematical statement, we start with this one. Mu is mu greater than 0. That's our claim. So if I wrote out here, if I was doing this on the blackboard, I would say claim mu greater than 0, complement mu less than or equal to 0. That's the other situation that it could be. Since I'm only really concerned if this passes this equal to 0, it's certainly true for the less than or equal to 0, so they just write that as equal to 0 in this text. And it's kind of a mixture of the two that you will see if you go on to other statistics courses. So once I know this, the mu equal to 0, less than or equal to 0, greater than 0, the equal part of it, I assign the null hypothesis, that's H0. H sub 1 is the alternate. So the claim can be either the null hypothesis or the alternate hypothesis. In this case, it's the alternate. But the alternate always tells us what test we're going to run, a right-tailed test. Okay? So our test statistic is the X bar minus mu 0 divided by S over the square root of N. So here I just get this. This is the mu 0 is the value we're using with the null hypothesis. So mu 0 goes with the H0 value. In this case, we're saying 0. So the T, just like a Z-score, this T-score is 3.144. Okay. When H0 is true, the test statistic T has the student's T distribution. I'll have to go to my A3 or use my calculator with the T distribution. The degrees of freedom is 75. Right-tailed test. So I would go and find the p-value. If I'm doing the p-value method, is to find the area under the student's t-curve to the right of 3.144. Yeah. Here's our picture. Go up here. So if we went to our TI-84, the 36 will give it to us. We find the exact p-value to be p is equal to 0.0012, and then we compare it to what value of the alpha. So at this, we're going to do the 0.05 is what we're comparing it to. This is less, so we can reject H0 at the alpha 0.05 level. So since we reject this possibility, here's the claim, we can conclude this is true because we've rejected this possibility, okay? So let's do the computing. If we had to do the computing p-values, the p-value of the test statistic T is the probability, assuming H0 is true, of observing a value for the test statistic that disagrees or strongly as or more strongly with H0 than the value actually observed. Okay, so it's basically the probability of seeing something more extreme than what we have got in terms of ours. So the p-value is an area under the student's t-curve with n-1 degrees of freedom. The area is in the left tail, the right tail, or in both tails, depending on the type of test. And remember, if I'm doing a two tails, once I get that area, the probability value for one side, I multiply it times 2. So I don't have to divide alpha by 2 to compare it. I've got it directly. Okay. Left tail, the p-value is the area to the left of t. Right tail, the p-value is the area of the right of t. And if I'm two-tailed, the p-value is the sum of the area to the left and to the right, which is twice. Since this is symmetric, it is just twice that value. Just multiply it times 2. If I go to a table, let me slide me down here so we can read through this. When using a t-table, sometimes we cannot find the p-value exactly. Instead, we can only specify that p is between two values. If it just happens to be there, we've got everything, we report it naturally. But many times it's between the two values, and we're just going to do is between this value and the other, between those two values that we've got. Okay? So here's another thing. In the last example, there were 75 degrees of freedom. And if you remember from previous work, the degrees of freedom in A.3 goes down to the left. Once we get out to larger and larger degrees of freedom, this thing starts expanding out because it doesn't change as much. With only small degrees of freedom, these values change very rapidly. But once we get down here, they're pretty much fixed. And once you get past 200, it looks just like the standard normal distribution. Okay. So if you go, and if you need 75 degrees of freedom, you have to back up one. Okay, so you need to go to the left. So you're going to do where there's more extreme values. So you would do the 60. The p-value, so we're going to do, here's this one. Degrees of freedom, I'm looking, the value was 3.144 was our t-test statistic. That lies between the 60, somewhere between here and here. So the p-value lies somewhere between 0.0025 and 0.001. Okay. This was for a right tail, so I would keep these numbers the same, and I would report it is somewhere between 0.001 and 0.0025. So we just keep that and not try to do any interpolation between the two values. So there's basically the picture again, p-value from a table for a two-tailed test. I would go through, find this, and then I would multiply that times 2. So if this was a two-tailed test and everything was the same, I got those values. Instead of reporting the 0.001 and 0.025 as the p-values, I would multiply both of these by 2. So between 0.002 and the 0.005, this multiplied times 2. That way, if I change the alpha value, the significance value, all I have to do is go compare these again to make sure. So if I went from 0.05 to 0.01, I'm still okay. But if I go less than that, I may have to have a problem and reject H0 or fail to reject. Okay. Here's another one. Generic drugs are lower cost substitutes for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The U.S. FDA is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of skin. As part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that's been absorbed into the skin is measured. The amounts of micrograms are, and here's the following. Here's the values. 2.632, 2.130, 3.1, 2.9, 3.7. How strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? So I want to find out if it differs. I want 3.5 micrograms to be delivered. I measure these things. Is it way more or way less? Either one of those we would want to reject the hypothesis that it needs to be 3.5. Okay, so that's the brand name. If this is significantly different, significantly being here's the alpha values that we compare to, then we reject that they can use it as a generic drug. Okay. Notice this is a small sample size, 1, 2, 3, 4, 5, 6, 7. How do I handle that? Well, I don't know if it is with their make, is it a normal distribution? Is it normally distributed? So I go and do a dot plot. Here's the values. I don't see any major, I mean, these are kind of grouped here in the middle, but this is not a large distance apart. So I don't think these are outliers. I wouldn't consider those outliers. There's no heavy skewness over on one side. Between 3.0 and 2.0 is 1, 3 to 4 is 1, so they're basically centered 1, 2, 3, 4, 1, 2, 3, 4 over here. So I'm going to call it, we will call it that it looks to be normally distributed. There's no reason not to, so we really need this value, we're going to use it. So the null and alternate hypotheses are, these are what we were trying to do. Is it 3.5? That's what we want. Well, it can differ, so the difference can be less than or equal to, so all we're going to do is test against it not being 3.5. The not being 3.5 is a two-tailed test. It could be less than or right than or greater than. So we compute the X bar and the S from the sample. We have those values, and they're calculated for us 2.9429, and S is equal to 0.4995. I calculate the test statistic. Again, mu0 is from our H0 assignment. H0 is the equality. The complement not equal is our alternate. That tells us the two-tail. Mu0 is that assigned to H0. This is the 3.5 value. Here was our X bar from the sample. There's our standard deviation. Small sample size n is equal to 7. Take the square root of 7. Here is the value of the t-test statistic, negative 2.951. What are the degrees of freedom that we're going to go to for table A.3? N equal to 7 minus 1 degrees of freedom, n minus 1. So that'll be 6 degrees of freedom. Okay. So here the alternate is two-tailed. The p-value is the sum of the area to the less of the observed t-statistic, the negative 2.951, or times 2 since it's symmetric. So using table A3, we'd go down. Here is the degrees of freedom 6. The two values closest to 2.951 in the row corresponding to 6 degrees of freedom go to 6. And here's the ones that's in between 2.447 and 3.143. And then I go up and I see what the p-value is for that, the probability across the top. The area to the right is 0.025. Area to the right here is 0.01. So I would multiply both of those by 2, 0.05 and 0.02. So the p-value, now I can compare it directly to our alpha, the 0.01. So we're checking at the alpha 0.01 value. Is these probabilities less? No. So we can't reject H0. The p-value is small enough to give us doubt about the truth of H0. However, because p is greater than 0.01, we do not reject H0 at the 0.01 level. So there is insufficient evidence to support the hypothesis that it was equal to the 3.5 micrograms. Okay. At the alpha 0.01 level, there is insufficient evidence or not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms. The mean may be equal to 3.5 or it may not. We just can't make a definitive statement about not being that. Okay, that we would reject it. So if I do the TI-84 plus, we went back through that, do the very same thing. This is one we did before. Simple random sample n greater than 30. We would run these things. This was greater than 0 or less than 0. This is the same one that we ran before, but it is just here's the result and here's how we run it on 84. So we're back to here. Okay. If I went to and entered everything here, it would give us this value of p at 0.0012 for a single tail. That would be the p-value, and again, we could reject that based on the 0.05. So the table, we had the two values, we had to multiply by 2 if it was a two-tail. In this case, it wasn't, it was a single tail. Okay. Here's how we can do it. If we go to t-test, so we go back into our stat on the 84, run a t-test. Here's our statistics. It was comparing it to 0. The mean was of the sample was 2.2. Standard deviation. What is the difference between these two? This one asks, if we did a z-test, it would be saying sigma x. What was the standard deviation of the population? Here we're doing a t-test. It's asking for the standard deviation of the sample. Give them the n. We wanted to do a right tail test. This is what we have to select here to tell it which kind of test we're going. And then we'd go down a tab and do the calculation. The result would be the p-value 0.001. It would give us that value, and directly we would compare it. Are we talking about at a 0.05 value or 0.01? Whatever the significance level was, we would compare that directly. That's less than 0.05, less than 0.01. We would reject. So that just gives us the information. We have to interpret it and reject it. So take a few minutes, make sure you understand what the outputs are. We will see in the future questions where here's the results of a software test. Go through and look at it and be able to interpret what the test tells you. Okay. Here's the generic drug. We went through there. This was mu equal to 3.5 versus mu not equal to 3.5. We didn't know if it was significantly more or less. We would do the very same thing, the t-test, but note in this version, when we entered everything, 3.5 was mu 0. That was what we're testing against. Our list, this would, if we put it in a list, we can run it through here with our data. We did the statistics, we could just put the values in there, but this did everything for us. If we say, here's the data, go to it, here's my 3.5. The list is L.1. Frequency is 1 each of these. We're doing the test is not equal to mu 0, so that's the two-tailed version that we want to do. Calculate, here's the result, the p-value. This is automatically multiplied by 2 when I'm doing a two-tailed test. So at the 0.05 level, I could reject H0. At 0.01, I couldn't reject it. Okay. So there's not enough evidence to conclude the mean amount of drug absorbed differs from 3.5 micrograms. Okay. So we failed to reject at the 0.01 level H0, which it was the mu is equal to the 3.5. At 0.05, at the alpha 0.05, we could reject that it was equal to that, that it was equal to the 3.5. The critical value method, remember we would go through, draw the curve, we would calculate the critical values based upon the alpha level. Left-tailed, I would do a negative T alpha, the alpha, the inverse value for the T statistic to get that. The critical value of T alpha, if I'm a right-tailed value, that's the positive value. And then if I'm two-tailed, I divide that alpha by 2, calculate the critical value for both the left tail and the right tail. So a computer software vendor claims that a new version of their operating system will crash less than 6 times per year on average. A system administrator installs the operating system on a random sample of 41 computers At the end of a year, the sample mean number of crashes is 7.1 with a standard deviation of 3.6. We're assuming they didn't say that they didn't say sigma. That's a new stuff. We're just doing the sample standard deviation. Can you conclude that the vendor's claim is false using the alpha is equal to 0.05 significance level? So they want to know, they claim that it's less than 6 times per year, okay? And here's the 7.1. So let's go through. We're going to see if it is less than or equal to 6 or greater than 6. So those are, we would go here, we would say their statement is less than or equal to 6. And here's greater than 6. So if we do this, this is actually less than 6 times, but we're going to use the 6. So if 6 or less, that would make sure that it's everything. Versus mu greater than 6, H0 goes with the equality, the alternate goes with the other, a right tail test, n's greater than 30, so we can go and we're going to continue with the test. We didn't know what the population standard deviation was. We have to use the t statistic, the t-test statistics, x bar minus mu 0. The mu 0 that we're comparing it to is the 6. We got a mean of 7.1, standard deviation is 3.6. So the t-test statistic is 1.957. Degrees of freedom, we did 41 minus 1, this 40. We would go A3 down here. We are looking for, so here we're going to do the critical value. So we looked at the 0.05 in the right tail. The critical value with 40 degrees of freedom would be 1.684. In this case, I'm doing the critical value. Here's the area that I'm looking for. I go across here. Here's the degrees of freedom, and this is the critical value that would give me 0.05. I'm going to plot the t-value, the t-test statistic, that 1.957 compared to that. So here's the 1.684. The t-alpha is the t-value, the critical value based on alpha 0.05. That was the 1.684. Here's the test statistic, 1.957. It is in that critical region of the tail. This is the rejection region in the tails, if the test statistic shows up there. Here is the fail to reject region. In this case, we would reject, who do we reject? H0. Okay. So we conclude that the mean number of crashes is greater than 6 per year. We reject the possibility that it is less than or equal to 6 based on our sampling. Okay. So that is, again, 8.3. Again, we were performing a test of a statement based on the population mean. All we've got is current sample data, but we can use that to possibly reject a statement or fail to reject a statement. Okay, and that's where we went through. 8.2, we know what the population standard deviation is. In this case, the sigma is unknown, so we use the sample standard deviation and use the student's t distribution for our values. Okay, so I hope you found that useful. We'll see you next time. We've got to do the population proportion still. Thank you.